Hey everybody, this is the lab alternative for activity 5.1. This is out of our Earth Science 3 book. And so if you're doing this activity, it means you were either absent when we did the original and you need to make it up, or quite possibly you didn't have a Chromebook, you were late to class and didn't get started on time. There's lots of possibilities that you might be doing the lab alternative. So our learning target today is we're going to determine how the pattern of earthquakes and volcanoes on Earth are related to the Earth's plates. So we've talked about earthquakes and we talked about volcanoes. We've talked quite a bit so far about the Earth's plates and the lithospheric plates and how they came to be. Now we're going to start to focus on what happens as a result of their interactions with each other, or the plates' interactions with each other. So specifically, we're going to look at earthquakes first in this lab, and then we're going to take a look at volcanoes. Now, if you're doing the lab alternative, you're going to see this at the top of it. It says alternative activity for students who are absent or can't complete the in-class activity. So what I'm asking you to do is double check your paper. If you are doing this, do you have the lab alternative? If not, you can complete the regular one, but just let your teacher know, because you're not going to have certain videos that's going to allow it. So let your teacher know if you do not have the lab alternative. Now, if you're in class and we're going through this live and all of a sudden you see this red marking and you don't look at it, you don't read it, you don't pay attention, and you do the lab on the alternative instead of the regular lab, well, you may get a 0 on it. I may count it as missing because I won't know that you did the lab alternative because you weren't supposed to do the lab alternatives. So just make sure you're completing the correct lab. So activity 5.1, we're going to determine how the pattern of earthquakes and volcanoes on Earth are related to the Earth's plates. So what I'd like you to do is answer these two questions. What do you already know about earthquakes? And what do you already know about volcanoes? So the expectation is just have at least a sentence for both, possibly two, maybe even three if you're advanced. So go ahead, pause the video, and just type something up. What do you already know about earthquakes? What do you already know about volcanoes? And then when you get done with those, unpause the video. All right, so hopefully you've got some good things down there. Is this something I can correct? No, it's really what do you already know. You should know something because we've been in this book for a while. So I do expect you to have something. I don't expect you to have, I don't know, I haven't learned anything about it, because we have in class a little bit anyway. So if you remember this map, we looked at this map early in the book. And originally we just looked at the yellow dots, the earthquakes. Then we looked at the red dots. Then we looked at the black lines showing the plate boundary. And then we had a map similar to this that showed them all. So here's a question for you. Based on this map that you see right here, what kind of patterns do you observe on this map? So go ahead, if you're doing a lab alternative, pause the video and write a couple sentences. What kind of patterns do you observe on this map? All right, so hopefully you have some good patterns. You might have talked about how a lot of the earthquakes and a lot of volcanoes seem to form in these long lines. And it's not a linear line where it's a straight line, but there's a pattern here where they seem to be on, most of them, a lot of them seem to be on the edges of plates, and a lot of them seem to be on these black plate tectonic lines. Again, these black lines show the outline of the plates. So there's certainly some that aren't on the plate boundaries, like up here, but a lot of them are on the plate boundaries. So that's probably one of the key patterns that you notice, that they come in clumps, that they're together, that they're on the edges of plates. Some of even appear to be in the middle of the oceans. So the next question, you're using this map too, how might geological events and features such as earthquakes and volcanoes be related to plate tectonics? Use any knowledge you have gained. So go ahead, pause the video and complete this by writing a sentence or two. All right, so hopefully you took your time and you have a couple solid ideas here. So basically it's the plate interactions. When these plates are sliding past each other, such as a transform fault boundary, if they are going away from each other, such as a divergent plate boundary, or if they're going towards each other, a convergent plate boundary. Whenever you have all these different interactions between plates, things are going to happen. The earth is going to move, and you're going to get earthquakes. You're going to get volcanoes, and that's what we're really going to start to focus on in this mini unit, this next unit out of the book. We're going to focus on earthquakes and volcanoes, and in our last unit, we're going to focus mainly on plate tectonics and the interactions of the plates. So if you were in class, what I would have you do is I would have you do an experiment. And this is one of those things that's really hard to simulate earthquakes in a middle school lab. It's hard to simulate earthquakes anywhere because it's hard to get or simulate something that shakes the entire planet or shakes the entire, surrounding area if it's a large enough earthquakes. But if it's large enough, it may not shake the entire planet that you can feel, but seismographs can actually pick up the seismic waves on the other side of the planet. So it's hard to simulate that. So we're going to do the best we can. And what we have for you is this. We took 2 wooden blocks and a plastic 50 milliliter beaker. And we put these blocks flat on the table side by side. And we put the water, the 50 milliliter beaker of water on one of the blocks. And what we did was we slid them past each other. And even that simple action of sliding past each other, you could see the water shaking. So just even a simple, interaction of 2 blocks sliding past each other shook the water in the beaker. So what I'd like you to do is take some time, watch both of these videos. They're short. One shows the side view of the lab happening, and the other one shows the top view of the lab happening. So go ahead, take a couple minutes, watch those videos. All right, so now that you've watched the videos, I want you to answer these questions. Now, if you didn't watch the videos, you're going to have a hard time answering these questions. It says, record your observations about the wooden blocks. So what did you observe? What did you see happening with just the wooden blocks? Then what did you observe about the water in the beaker? So if you have to re-watch the videos, go ahead and do that. And I expect you to have at least a sentence for both. Don't have something, just one word, but a good solid sentence for each. And then unpause the video when you're done. Excellent. So what did you notice? Did you notice that even though the wooden blocks seemed to go pretty smoothly, every once in a while they would seem to catch each other? And it would kind of like stop for a brief second, then it would like jerk forward as it continued on its path. And then with the water in the beaker, did you notice at the beginning, before I started moving them, the water was still. There wasn't very much movement, if any at all. But once I started sliding it, even though the blocks seemed to be pretty smooth, you can see that there was a lot of shaking of the water. And that's what I wanted you to observe. So moving on to the next set of questions. What event did you just simulate? Why do you think this? What do the wooden blocks in the beaker represent? And what are the similarities of this simulation to the real world? What are the differences? So go ahead, pause the video and answer these questions. You should have a solid sentence for each, keeping in mind that questions 1 and 3 actually have 2 questions each. So you should have 2 sentences here and 2 sentences here answering both of those. So go ahead, pause the video and unpause it when you're done. Excellent. So what events did you just simulate? Well, you simulated the Earth's plates moving. You basically simulated a volcano happening. And the water, so why do you think this is? Well, we can't simulate the actual earthquake. So this is the best we can do. So plates can slide past each other, and that's what we simulated. So why do you think this? Well, plates can slide past each other. Wooden blocks can slide past each other. The plates can sometimes catch and lock in place, so can the wooden blocks. Number 2, what do the wooden blocks and beakers represent? Well, the wooden blocks represent the plates or the lithospheric plates, and the beaker represents, anything on those plates. It could represent buildings, it could represent lakes, it could represent soil, lots of different things. So when the earth is shaking, you could see the water shaking. Buildings are going to shake, the ground's going to shake, lots of things are going to shake when there's an earthquake. So what are the similarities of this simulation to the real world? Well, plates can slide past each other, so that's the similarity. And sometimes they go pretty smoothly, but sometimes they catch and you have a much more violent earthquake versus a smaller earthquake. In the simulation, we got the water moving. It was not calm anymore, that it was vibrating back and forth. And you're going to get that in the real world. The difference is, well, the water moving in the two blocks, it's not going to be a perfect simulation because they actually move together fairly smooth on each other. And that's because we've been using these same blocks for several years now. So they've, rubbed to the point where they're pretty smooth. That's not going to happen in the real world. The plates are going to lock up and they're going to catch. And even though the plates move at about the same rate as your fingernails grow, on these plate boundaries, they don't always move. For years and years, they may not move. And all that force, all that tension, all that elastic energy is, building up, building up, building up, and all of a sudden it snaps. And it happens really fast, and it moves. It could move, as many as, a few meters or more. So it's not just going to move a few centimeters, which it could, but a lot of times it's going to be much more. The difference is, again, we're not going to have all the earthquake damage. We're not going to have the shaking of all the ground, all the land. The school's not going to be destroyed because there was an earthquake here. So it's much, much more gentle in the lab. So that way we can study it and we don't have to actually experience the real one. Now, if you want to experience real one, how do you know when an earthquake is going to happen? You could go out to California and they have lots of earthquakes. A lot of them you don't feel, but you might be out there for months and not feel an earthquake at all. And all of a sudden you feel a few within a few days. All right, so moving on. So that was the earthquake, and that was just an introduction to earthquakes. We're going to spend a lot more time on earthquakes. Now, let's talk about volcanoes. So what I'm going to do is, if you are doing the lab alternative, the copy that's online, you'll actually have a link to these 3 videos. What I would expect you to do is pause the video and watch each of those videos. I think combined it might be 7 or 8 minutes worth of videos. Then once you get done, go ahead and answer the making sense questions. All right, so let's go through these making sense questions and see how you did on those. So number 1, what happens when 2 plates move towards each other? Now, you don't have to write all this down. Look at what you have. If it basically is summarizing this, that's great. I just wanted to make sure that we were really detailed with the answers. So when continental and oceanic plates move towards each other, one plate moves underneath the other one. The thinner plate, which is typically the oceanic plate, was the one that moved underneath the thicker plate. The thinner plate then melts as it subducts into the earth. The melted rock moves upwards through the neighboring plate because it is less dense than its surroundings. This causes a volcanic eruption on the surface. This is a convergent plate boundaries, or plate boundary. So we've learned about the different densities of the plates. We learned that even though the continental plates are thicker than the oceanic plates, they're less dense. The oceanic plates that are, basaltic type rocks, they tend to be much more dense and they will sink if they come in contact or if they come head to head with the continental plate, just because it is more dense. And as a result, the thinner oceanic plate subducts underneath the, less dense continental plate. And as it starts to melt, not all the rock melts at the same time. Different rocks have different melting points. So some of the less dense material within the oceanic plate will start to melt first. And then this melted rock will make its way up to the surface, create volcanoes, and you're going to have volcanic eruptions. A good example of this would be the islands of Japan were created in this way. So when we look at the next question, 2, what happens when 2 plates move away from each other? And we've already studied this quite a bit this year. When 2 plates move away from each other, a ridge forms and the melted materials that comes through at the surface solidifies, forming rocks. And the example that we looked at was the Mid-Atlantic Ridge. We took a look at what happened. We looked at several simulations that show as the plates are moving apart, new molten rock is going to be coming up and taking its place. And that all has to do with the convection currents. So as more and more material continues to melt and comes through at the spreading center, the plates get pushed away from each other. And this is called, it's called seafloor spreading, but this is a divergent plate boundary. And we studied this quite a bit already this year. When I look at the next set of questions that you've already answered, why do you think this happens, and what happens when two plates move alongside each other? So why do you think this happens? Well, plates move because they're riding on a slowly convecting solid rock of the mantle. And we talked about this being the asthenosphere. It's a conveyor-like material or belt where it's constantly moving. It's not very fast, but it is moving, and it's pulling the plates along with it. Now, as the magma pushes up through, it helps to move the plates. We also talked about the ridge push theory, slab pull, but we're not going to get into detail with that. So this is why the plates are coming together, and this is why the plates are moving apart, depending on where you are within that convection current. So you come in, are you talking about a place where the convection currents come together and then spreading apart? Or are you talking about where two convection currents are coming together, and that's where you're going to have the convergent plate boundaries? So what happens when two plates move alongside each other? And this is what we actually simulated today, or you saw in the video. When the two plates move alongside each other, they rub up against each other and the earthquakes occur. And this is called a transform plate boundary. And when plates are moving by each other, they're not necessarily one's not going to subduct underneath the other one. But what will happen, just like in convergent divergent plate boundaries, is sometimes the rocks will catch each other and the pressure will build, and then all of a sudden it slips, and that's where you're going to get your earthquakes. If along these plate boundaries everything was smooth and it was all greased, then you could just go and it would never catch. You would never have earthquakes, and that would be awesome. All right, so make sure that you let your teacher know that you finish this lab. Let them see, or her see, that questions are done and completed. So just bring your Chromebook up. Don't just email your teacher. Don't just finish it and not say anything. That way, if it was used as a grade point check, you will get credit for it. And as always, if you have any questions, make sure you ask. Thanks. Bye.